Okay, what's the molar mass of CO2 in grams to 4 significant digits? I'm going to point this out to you right now because your paper says 3, and I want it to 4, not to 3. There's a little typo there. So, same thing as before. You have to write down how many of each element you have. You have 1 carbon, and you have 2 oxygens. So 1 times 12.011 and 2 times 15.999. So that's 12.011, and that is 31.998. And then we add those together, it gives you 44.009. And then it says to 4 significant digits, okay, or 4 significant figures. So 1, 2, 3, 4. Okay. Which means that we're taking these, the 9's going to round that 0 up. So you get 44.01 grams. And that's the mass of CO2. Okay. So bubbling in, we have positive 44.01. Positive 44.01 grams. Remember to bubble all the way in. I'm having a hard time doing that with my stylus. Okay. Number 26. Vinegar, a common household item, is used in cleaning, cooking, baking, and meat preservation. Vinegar contains acetic acid, CH3COOH, which gives vinegar its sour taste and pungent smell. What is the percent composition of carbon in acetic acid? Okay, well, in order to find percent composition of carbon, we have to find the molar mass of CH3COOH. Okay, so starting with carbon, hydrogen, and oxygen. Those are the 3 elements that we have in there. We have carbons in 2 different places. If you look here, there's a carbon there, and there's also a carbon in the beginning. So we really have 2 carbons, okay? And the same goes for the hydrogen. There's hydrogen 3s there, and then there's 1 on the end, which means that we actually have 4 hydrogens, and we have 2 oxygens right next to each other. So that means we have 2 times 12.011, and we have 4 times 1.008, and we have 2 times 15.999. So we get 24.022, and we get 4.032, and we get 31.998. And we add those guys up, and we get 60.052. Alright, now to find the percent composition of carbon, all you do is take your mass of carbon, which is 24.022, and you divide it by whatever the total mass is, in this case 62 or 60.052, and you multiply by 100 because you're saying that you have this much mass of carbon per total of the element, of the compound. So that's going to give you your percent. A percent, remember, is always some amount out of the whole. Alright, so that gives us 40.009, blah, blah, blah. Okay. And we can take this to 5 significant digits. Okay, so that's going to be 40.001%, or just 40%. Number 27. What mass of sulfur would have precisely 4.7 times 10 to the 22nd atoms of sulfur? Okay, so guess method here. We know that we're given 4.7 times 10 to the 22nd atoms of sulfur, and we know that we're trying to get to, sorry, I'm going to move this down a little bit. We know that we're trying to get to grams because it says mass of sulfur. Okay, well, in order to get from atoms into mass, we have to do two conversions. In order to get from atoms, we have to go to moles first. So it's always 1 mole of our substance, in this case sulfur, is equal to 6.02 times 10 to the 23rd atoms of sulfur. Use Avogadro's number. That's one conversion statement. And then once we're in moles, we need to go to mass using molar mass. So that we have to look up on the periodic table. This is easy since it's just an element. We don't actually have to calculate molar mass. We can just find it on the periodic table. It is 32.066 grams. Okay. So then we're doing our equation. We've got two conversion statements, or equivalent statements, which means this is a two-stepper. We're starting with atoms of sulfur because that's what we're given up here. Alright, and then our first conversion statement we need one that has atoms of sulfur in it, and that's this first conversion statement here, because right here it says atoms of sulfur. Remember, whenever you're converting, you always want the units that you're trying to get out of to be on bottom, so that means atoms of sulfur is going to be on bottom, which means 1 mole of sulfur has to be on top, because that's the other half of this equivalent statement. So we've used both of those. And then we're on to our second equivalent statement. Our second equivalent statement, 1 mole is to grams. Well, again, we've got moles on top here, which means that we need to have moles down here. So moles of sulfur on bottom, grams of sulfur on top. Okay, so now we can go ahead and put our numbers in for our solve. For our substitute, 4.7 times 10 to the 22nd atoms of sulfur. 1 mole of sulfur over 6.02 times 10 to the 23rd atoms of sulfur, and then 32.066 grams of sulfur over 1 mole of sulfur. Okay, so what are we going to be doing? This number's on top, this number's on bottom, this number's on top. So this is going to be 4.7 times 10 to the 22nd divided by Avogadro's number multiplied by 32.066. Remember, when you put these in a calculator, to make sure you put them in parentheses or it will not come out correctly. Okay, so you get 2.5035. And if we look at significant digits, this has 2, this has 3, and this has 5, so our answer is going to go to 2. So final answer is 2.5 grams of sulfur. Alright, how many molecules are there in 2.5 moles of water? Okay, so we're given 2.50 moles of H2O. Trying to get to molecules of H2O. Molecules is a number, which means we use Avogadro's number to go between these. Remember, it's always 1 mole is equal to 6.02, times 10 to the 23rd molecules of water. And then we're done. So this is a one step. We started with moles of water. That was our given. And we're trying to get into molecules, which means moles has to be on bottom. Okay, so these two units cancel out and we're left with molecules of water. So substituting in, our given number always goes first, and then we use our equivalent statement. So that means that we have 2.50 moles of water 6.02 times 10 to the 23rd molecules of water over 1 mole of water. So these two are right next to each other. All we're doing is multiplying. Oh my goodness, I apologize. That looks terrible. 2.50 by 6.02 times 10 to the 23rd. And you get 1.505 times 10 to the 24th. The last thing is significant digits. So if we look at our significant digits, this has 3, this has 3. Both of these have 3, so we need our answer to go to 3. So our final answer is 1.51 times 10 to the 24th molecules of water. Okay, how many moles are there in 8.50 times 10 to the 24th molecules of sodium sulfate? So we are given 8.50 times 10 to the 24th molecules of Na2SO3. Okay, and just FYI, that is named incorrectly. That should not be sulfate, that should be sulfite, because SO3 is sulfite. It's a typo, but it's wrong on your test too, so just understand. Alright, and I'm going to move that down a little bit. Okay. So we're trying to get into moles of Na2SO3. That's what we don't know. So molecules to moles, same thing as before. 1 mole of Na2SO3 is going to be equal to 6.02 times 10 to the 23rd molecules of Na2SO3. Avogadro's number, always to go between atoms, molecules, formula units, ions, whatever a number is. That's what we're doing. This is, again, just a one step. So they are given molecules to begin with, which means molecules has to be in the top left. Okay, which means that molecules has to go on the bottom here, so that our units cancel, which means that it's going to be moles of Na2SO3 on top. And again, that's just because that's from our equivalent statement. Molecules and moles are opposite of each other. So substituting in, we have 8.50 times 10 to the 24th molecules of Na2SO3 over 1 mole of Na2SO3, and we have 6.02 times 10 to the 23rd molecules of Na2SO3. Okay, so we have a number on top, a number on bottom. That means we just divide them. times 10 to the 24th. Remember parentheses. 6.02 times 10 to the 23rd. Dividing those two numbers. You get 14.1196. Okay, so the last step is to look at our significant digits. This has 3. Yes, that 0 does count because we had a decimal there. And numbers in front of this times 10 to the whatever always count. And we've got 3 here. So that means our final answer also has to have 3 significant digits to go to the correct place value. So that means that our final answer is going to be 14.1 moles of Na2SO3, or sodium sulfite, not sulfate. Okay, so positive 14.1. Okay. How many chlorine ions are there in 400.5 grams of AlCl3? Alright, this is a little bit more complicated because we've got chlorine ions here and we've got a compound aluminum chloride. So this means we're going between two substances, so this is full-blown stoichiometry. This isn't just a little one-step conversion anymore. We're given 400.5 grams of aluminum chloride. Okay, and we're looking for chlorine ions. So first of all, we got to get out of the mass or grams of aluminum chloride into moles of aluminum chloride, which means that we have to do molar mass. And this one we have to actually calculate. We've got 1 aluminum, we've got 3 chlorines. The mass of aluminum is 26.982. The mass of chlorines is 35.453. So that's just 26.982. And then we have to add that to our mass of our, which is 106.359. So adding those two together, you get 133.341. So we put that up in our space up here. Okay, so that's one conversion statement. That gets us into moles of aluminum chloride. Then we have to use our subscripts so that we can compare the moles of aluminum chloride with the moles of chlorine ions in that compound. So for every 1 aluminum chloride, if we look at our subscripts, there are 3 chlorines. Okay, so that means that there are 3 chlorine ions for every mole of aluminum chloride, or 3 moles of chlorine ions for every mole of aluminum chloride. Okay, so that gets us into moles of chlorine. So far we've gotten out of mass into moles of aluminum chloride, and then out of moles of aluminum chloride into moles of chlorine ions. The last step is to get out of our moles of chlorine ions. So a mole of chlorine ions is always going to be Avogadro's number to get to the actual ions, a number. So this is a 3-step just to get to our chlorine ions that we're looking for. So to do our equation, we're given grams of aluminum chloride to begin with, which means that we need grams of aluminum chloride on bottom and moles of aluminum chloride on top. That is this first conversion statement here, grams to moles of aluminum chloride. Then we're going to use the second conversion statement to get out of moles of aluminum chloride into moles of chlorine ions. So always whatever we're trying to get out of goes on bottom so that the units cancel. Okay, so if we look, grams cancel, moles of aluminum chloride cancel. Now we're on our last conversion statement. We need to get out of the moles of chlorine and into chlorine ions. So moles of chlorine on bottom and chlorine ions on top. So substituting in, we've got 400.5 grams of AlCl3 over 1 mole of AlCl3 and 133.341 grams of AlCl3. And again, those numbers came from this first conversion statement. So 1 mole, 133.341 grams, 133.341 grams. Now we're on to the next one. If we look, we've got a mole of AlCl3 and 3 moles of chlorine. So we're going to put those there. So that means that 3 moles of the chlorine goes on top, 1 mole of the aluminum chloride on the bottom. And then our last one, 1 mole of chlorine on bottom and 6.02 times 10 to the 23 chlorine ions on top. And again, that came from here. Alright, so we used all 3 conversion statements. Now it's just the math. Number that we were given divided by mass times 3 moles times Avogadro's number. Remember to put the Avogadro's number in parentheses, or you will not get the right answer. Alright, so you get 5.42446, so on and so forth, times 10 to the 24th. Last step is our significant digits. This has 4, this has 6. Remember, these are perfect. This has 3, so our answer needs to go to 3 based on the 6.02. Okay, so final answer, 5.42 times 10 to the 24th chlorine ions. How many hydrogen atoms are there in 7.3 moles of ethanol? Okay, and again, this is a full-blown stoichiometry problem. So we are given 7 point, and the reason why I know that is because we're going hydrogen and we've got ethanol. We got 2 different substances here. So 7.30 moles of C2H5OH. Alright, so first thing we need to do is get out of the moles of ethanol, the C2H5OH, okay, and into moles of hydrogen. So 1 mole of the compound, and we've got to figure out how many moles of hydrogen are, and that's just subscripts. But we need to be careful on this because there's hydrogen here and there's also hydrogen here, which means we actually have 5 plus 1 hydrogens, or 6 hydrogens for every 1 compound, which means that we've got 6 moles of hydrogen for every mole of ethanol. Okay, that gets us into moles, and then it asks us to go to atoms. So that's Avogadro's number. Once we've got moles of hydrogen, then we can use Avogadro's number to go into atoms of hydrogen. So this is just a 2-step to get to atoms of hydrogen. So we're starting with moles. That's what we were given. Moles of C2H5OH, or ethanol, which means that we need moles of ethanol on the bottom so that it cancels, and moles of hydrogen on top. And remember, I'm using this first equivalent statement. This is the one with moles of ethanol in it, so we need these moles of ethanol to cancel here and here. Okay, now we're in moles of hydrogen, which means I need moles of hydrogen on bottom so that it cancels, and atoms of hydrogen on top, because that's what we're looking for. So substituting in, we've got 7.30 moles of ethanol, C2H5OH. We've got 6 moles of hydrogen for every mole of C2H5OH, or ethanol. And 1 mole of hydrogen is equivalent to 6.02 times 10 to the 23rd atoms of each. Okay, so again, where did I get these numbers? This is a given, so it goes here. Our first equivalent statement, moles to moles, moles of hydrogen, moles of ethanol. So there's 6 moles of hydrogen, 6 moles of hydrogen, 1 mole of ethanol, 1 mole of ethanol. And then we're on to our second equivalent statement, 6.02 times 10 to the 23rd atoms, and 1 mole of hydrogen, 1 mole of hydrogen. Okay, so what are we doing with our numbers here? We got 7.30 times 6 on top times 6.02. So all of our numbers on top we can just multiply straight across. 7.30 times 6 times, remember to use parentheses, 6.02 times 10 to the 23. And you get 2.636 times 10 to the 25th. Alright, so last step is sig figs. 3, these are perfect. Mole to mole ratios are always perfect. And 3. So our answer needs to go to 3, which means here, the 6 is going to round the 3 up, so you get 2.64 times 10 to the 25th atoms of hydrogen. Solid zinc oxide is added to hydrochloric acid to form zinc chloride in water. How many moles of zinc chloride will be produced when 112 grams of zinc oxide is used? Alright, so we're given 112 grams of zinc oxide. I apologize. Before we do this, we need to write the equation. I forgot, I got ahead of myself. So zinc oxide, zinc is 2 plus charge, oxygen is a 2 minus charge, so it's just zinc, ZnO, plus hydrochloric acid. This is hydrogen, this is chlorine, chlorine is -1, hydrogen is +1, so you get HCl. And that goes to zinc chloride, ZnCl. Zinc is a 2 plus charge, chlorine's a -1 charge, so when we switch those we get ZnCl2. And it says in water plus H2O. Okay, so then balancing, if we look, we've got 1 zinc and 1 zinc, 1 oxygen, 1 oxygen, 1 chlorine, 2 chlorines. We're not balanced. So if we put a 2 in front of here, 1 zinc, 1 zinc, 1 oxygen, 1 oxygen, 2 hydrogens, 2 hydrogens, 2 chlorines, 2 chlorines. Everything is balanced. Okay? The states on this is solid, because it says solid. Acids are always aqueous. Zinc chloride, if you look at your solubility rules, is aqueous. And water is liquid unless it says vapor. So now that we've got our balanced equation, now we can go. Okay. So we've got 112 grams of zinc oxide. And it asks us to find how many moles of zinc chloride, which means that we're going to have to go from zinc oxide into zinc chloride. So the first thing we need to do is get out of grams of zinc oxide, and the only way we can do that is to go to moles, which means that we have to calculate the molar mass of zinc. So we've got 1 zinc, we've got 1 oxygen. The mass of zinc is 65.38. The mass of oxygen is 15.999. We add those two together, and we get 81.379. Okay, and so that gets us into moles of zinc oxide. Once we're in moles of zinc oxide, then we can go into zinc chloride using our coefficients. There's nothing in front of either one of these, which means it's a 1-to-1 ratio. So that means that if we compare zinc oxide to zinc, write this a little bit differently. Alright, So if we compare that, that means that we've got 1 mole of zinc oxide, 1 mole, keep forgetting the right mole, 1 mole of zinc chloride. Okay, well, now if we look, we got out of grams into moles of zinc oxide, and then out of moles of zinc oxide into moles of zinc chloride. The last thing is it says how many moles of zinc chloride do we need? Well, moles of zinc chloride, we're done. So at this point, we can go ahead and set up our equation. So we're given grams of zinc oxide, which means we need grams of zinc oxide on bottom. If we look at our equivalent statement, grams of zinc oxide here, moles here, which means that moles of zinc oxide has to go on top. Since we've got moles of zinc oxide on top, that means the moles of zinc oxide needs to be on bottom from this equivalent statement, which means moles of zinc chloride is going to be on top. And it needs to be because that's what we're trying to find. Always what we're trying to find on top, always what we're trying to get out of on bottom. So if we look, grams cancel, moles of zinc oxide cancel, we're left with moles of zinc chloride. It's exactly what we want. So now we can substitute in our numbers, 112 grams of zinc oxide, 1 mole of zinc oxide is 81.379 grams of zinc oxide, 1 mole of zinc chloride to 1 mole of zinc oxide. So what are we really doing here? Our original number, 112. This is on bottom, divide. Everything else is 1, so we can ignore it. So really, all we're doing is taking 112 and dividing it by 81.379. And when you do that, you get 1.3762. Last step is to get significant digits. This has 3, this has 5, so we're going to 3. So the 6 rounds the 7 up, we get 1.38 moles of zinc chloride. Okay. So number 33. Photosynthesis is the process through which water and carbon dioxide are converted to sugar and oxygen. This sugar is then becomes a source of energy for cellular respiration. How many moles of carbon dioxide are required to produce 3.25 moles of glucose? Record your answer and fill in the bubbles on your answer document. Be sure to use the correct place value. Use guess. All right, so correct place value, of course, remember that means significant digits. Okay, so starting with the fact that we are given 3.25 moles of glucose. That's what we're trying to produce. Oops, I don't want to write glucose. We want to look at the formula. Glucose, C6H12O6. And I write C2. Wow. Having problems this morning. Sorry, guys. C6H12O6. All right. And how many moles of carbon dioxide is what we're looking for. So that means that we're trying to get from moles of glucose into moles of carbon dioxide, which means that we need to use the coefficients. So we know that there's so many moles of glucose, C6H12O6, and so many moles of carbon dioxide. And we just use our coefficients for that. So there's 6 moles of carbon dioxide, and there's nothing in front of the glucose, which means that it's a 1. So that means for every mole of glucose, there are 6 moles of carbon dioxide. Well, we're trying to go from moles. We've given moles. So this is actually only a 1-step conversion, even though it's full-blown stoichiometry, because we're going between 2 different substances. So this actually isn't too hard. So we've got the moles of CO2 that we're looking for, and then we can just go ahead and set up our equation. We're given moles of glucose, and then we know that we're going to want to get out of that and go into moles of CO2. So we're given moles of C6H12O6, which means that moles of C6H12O6 needs to be on bottom, and moles of CO2 need to be on top. So substituting in, we got 3.25 moles of C6H12O6 and 6 moles of CO2 for every 1 mole of C6H12O6. And remember, I got these numbers. This is the given. 6 moles of CO2, 1 mole of C6H12O6. Alright, so solving, really all we're doing, if we look, both these numbers are on top, we can ignore the 1, is we're just multiplying 3.25 by 6. And we get 19.5. Last step is to look at our significant digits. We have 3 here. Remember, mole-to-mole ratios are perfect, so we're just worried about the 3, which means our answer needs to go to 3, and that has 3, so all we have to do is put our units on there. So it's 19.5 moles of CO2. Bubbling in, our final answer, positive 19.5, positive 1.9 5. You need to do a better job bubbling in than me. Okay, next one. 34. What is the molecular formula of a compound that has a molecular weight of 240 grams? We're given a 5-gram sample, contains 2 grams of carbon, 0.34 grams of hydrogen, and 2.69 grams of oxygen. Alright, so you need to recognize that this is a molecular formula problem, which means that we have to find the empirical formula. And remember the little trick for empirical formula: percent to mass, mass to mole, divide by small, multiply till whole. Well, percent to mass, we don't have percentages, we're already given masses, so we can skip the first step and we can just write down the masses that we have. For carbon, we have 2.0 grams, and for hydrogen we have I'm gonna actually move this down a little bit here and rewrite this. So carbon, we have 5.00 grams, and hydrogen, and the reason why I'm spreading this out is, so, oops, not 5 grams, 2 grams. 5 grams is the whole sample. Alright, so we have 2 grams of carbon, and anyways, the reason why I'm moving this down is so that I have room to do the mass to mole part. 4 grams of hydrogen, and oxygen we have 2.69 grams. Okay, so remember, mass to mole, to go from mass to mole we have to set up our T-chart, which means molar mass. So 1 mole of carbon is 12.011 grams, which means we're taking the 2 and dividing it by 12.011. Alright, 1 mole of hydrogen, when you look at the periodic table, is 1.008 grams of hydrogen, which means we're taking the 0.34 and dividing it by 1.008. And then the 2.69 grams of oxygen, 1 mole of oxygen over 15.999 grams of oxygen, straight from the periodic table. So we're taking the 2.69 and dividing it by 15.999. Alright, so if we divide each of those out, 2 divided by 12.011 is 0.1665, and we're just going to take that out a few places past the decimal to make sure that we don't have any error. And hydrogen is 0.3373, and oxygen is 0.1681. Okay, so if we look, smallest number is carbon, 0.1665. So then the next step is to divide by small, which means everything has to be divided by 0.1665, 1665, 1665. So obviously this is 1.3373 divided by 0.1665 gives us 2.03, and 0.1681 divided by 0.1665 is 1.01. Alright, so now what we're doing is we're looking at 1, 2.03, and 1.01, and we're deciding, are they close enough to whole numbers, or do we need to multiply to a whole? And 2.0 is 2, and 1.01 is 1. So we already have our whole number ratios. So our whole number ratios, carbon, hydrogen, and oxygen, 1 to 1. So that's our subscripts. So the empirical formula is CH2O. Remember, we don't have to write the subscripts for the ones, okay? So that's just to get the empirical formula. This asks us to find the molecular formula. So I'm actually going to go to the next page to finish this problem out, because otherwise I won't have enough room. The first thing that we need to do is find our molar mass for this empirical formula. So we've got 1 carbon, we've got 2 hydrogens, we have 1 oxygen. And the reason why we're finding the empirical molar mass is so that we can compare that to the molar mass that we were given experimentally. So that's 12.011, and that's 2 times 1.08. Should I erase that and make that better? 0.8, and that's 15.999. Alright, so we have 12.011, and we have 2.016, and we have 15.999, and we need to add all those together, and we get 30.026. Okay. Okay, so now that we have the the empirical molar mass of, this is the empirical molar mass, now we can compare that to the experimentally found molar mass, which was 240. So we have experimental molar mass of 240 grams per mole, and we have this one of 30.026. And remember that this is the experimental always on top, and empirical that you find always on bottom. So we take our 240 and we divide it by 30.026 to get a number close to a whole number. So we get 7.99, which rounds off to 8, which means that we need to take all of our subscripts and multiply them by 8. So that means that for carbon, hydrogen, oxygen, we have 1 times 8, 2 times 8, 1 times 8. So the empirical formula is C8H16O8. Okay, next one, 35. An unknown organic molecule with an empirical formula CXHY is analyzed through combustion and determined to be 79.85% carbon. What is the value of the Y subscript in the empirical formula? Record your answer and fill in the bubbles on your answer document. Be sure to use the correct place value. I apologize, I forgot to put the bubble on this one. Or actually, no, maybe I put it on the next slide in case we didn't have room, which we're probably not going to use it because I wasn't sure how much space this would take up. But anyways, to start this problem, we know that we have, for carbon, 79.85%, okay? I'm going to erase this. Sorry. Looks ugly. Okay, so carbon, we have 79.85%. Remember, first step is percent to mass, okay? And we know that our other element on here is hydrogen. Well, to figure out how much hydrogen there is, we know that this is always out of 100%. So we just take our 100 and we subtract the 79.85 from it to figure out what the hydrogen is. So 100 minus 79.85, only if I can put that in the calculator, right, is 20.15%. Okay, so once you go from percent into mass, then remember you're doing mass to mole. Okay, so these this is 79.85 grams, and this is 20.15 grams. Okay, so drop down here. Carbon, we know, is 79.85 grams. So remember to go to go into moles, we have to have grams on bottom, and we use the periodic table. 12.001 grams per 1 mole of carbon. Okay, and hydrogen, we have 20.15 grams. So for every mole of hydrogen, there's 1.008 grams of hydrogen. So all we have to do is divide these out. 20.15 by 0.008. Okay, so 79.85 divided by 12.011 is 6.648, and 20.15 divided by 1.008 is 19.990. Alright, so the 6.648 is obviously the smaller one. So we're going to divide both of them by 6.648. So remember, divide by small. 19.990 divided by 6.648 is 3.01, and this is obviously 1. So this is another situation where we don't have to multiply by whole, because, I'm going to erase that and make that prettier. 3.01 is basically 3, okay? So we know that we have 1 carbon, and for hydrogen we have 3 of them. So our empirical formula is CH3, okay? And then it asks what the subscript Y would be for hydrogen. Well, we know that since we have CH3, this is our subscript for the Y, if you will, on the hydrogen. So to bubble in, positive 3. And that's all you have to do. You don't have to put a decimal if you don't want to. You can if you want to. But it's just 3. Okay? Alright. Next one. During the combustion of methane, this is number 36, CH4, 1 mole of methane gas combines with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water vapor. Write the chemical equation that correctly represents the combustion of methane described above. Okay, this is actually so easy because it gives you everything. 1 mole of methane, and it tells you the formula. And it says 2 moles of oxygen. And it even tells you the formula. You have to remember that it's diatomic. And it says produces 1 mole of carbon dioxide and 2 moles of water vapor. So all you have to do really is remember what the formula for water is, which I'm going to kill anybody in my class that can't remember that. So we have the combustion of methane, okay, and it's 1 mole, so nothing goes in front, plus 2 moles of oxygen. And produce, remember, means arrow, yield. And we have 1 mole of carbon dioxide, so we don't have to put anything in front of that, plus 2 moles of water vapor. All right, so we know water vapor means gas, carbon dioxide is always a gas, oxygen is a gas, and methane, gas. So we know the states of everything. Everything is a gas. Okay, so that is the correct chemical equation. Super, super easy. As long as you read, it gives you everything in there. All right, 37. Write the balanced chemical equation describing the formation of water. Okay, well, we know water is H2O. We know we're forming it, so that means that it is our product. Well, there's only two things in water. There's hydrogen and oxygen. You need to remember that both hydrogen and oxygen are diatomic when they're in elemental form. So that means that we have hydrogen plus oxygen coming together, okay? And then we have to balance this, all right? So right now, we have 2 hydrogens and 2 hydrogens. And in oxygen, we have 2, but we only have 1, okay? Which means that we need to multiply this by 2, so coefficient in front of 2, which means we also need to multiply the hydrogen by 2. So now we have 4 hydrogens on our product side and 2 oxygens on our product side. So the oxygens are balanced, but if we look here, our hydrogens aren't. We have 2, but we have 4 on our product side. So we multiply our reactant side by 2, so that it also equals 4, and then that's our balanced equation. So we have 2H2 plus 1O2 yields 2 waters, and that is the equation for the formation of water. All right, classify the following reactions as combustion, decomposition, double replacement, single replacement, or synthesis. Okay, very easy. We have one reactant, and it's yielding more than one product. This is decomposition. Okay, we have one product and more than one reactant, so this has to be synthesis, or combination, as it's sometimes called. Here we have an element by itself, and in the end we have the other element by itself, which means that it's being switched. This is single replacement. And then on the last one, if we look, we have oxygen as a reactant, so this is combustion. All right, 39. What is the change in oxidation number of sulfur in the reaction shown below? Okay, so we really only have to worry about sulfur. Sulfur by itself is an element. Elements always have an oxidation number of 0. All right, and then we're looking at sulfur dioxide here. Well, you have to remember that oxygen, when it's in compound, has an oxidation number of -2, and then we can figure out what sulfur is. That's Rule 8, finding the individual elements from a compound. We know compounds always have to equal 0. So we have 1 sulfur, and we have 2 oxygens, and 2 oxygens, and we know that the compound has to equal 0. We don't know the charge on sulfur, but we know the charge on each oxygen is -2. So we have sulfur, can get rid of the 1, is -4 equals 0. 2, and the reason why I did that is 2 times -2 is -4, so this is -4. So if we add 4 to both sides, we get sulfur has a +4 charge. Okay, so the change in oxidation number, we went from 0 to +4. So our change in oxidation number is +4. It's +4, which means it lost, so sulfur was oxidized. All right, last problem on the whole review. The base barium hydroxide neutralizes the acid, and that is sulfuric acid, H2SO4, and we know that's sulfuric acid because of the sulfate. So we have barium hydroxide and sulfuric acid. What salt is produced? Okay, well, remember, when you have a base and an acid come together, that it's double replacement, which means that the OH and the H always go together, and then the other substances go together. So that means you have to put the barium and the sulfate together. You have to understand that this is a metal and a polyatomic anion coming together, so this is charges. Barium is in group 2, so it's a 2+ charge. Sulfate has a 2- charge. It comes from the polyatomic list if you can't remember it. So that means you get Ba2SO4 2 parentheses, but both 2's can cancel out, which means that it's really barium sulfate, BaSO4.
Good morning.